Good morning. We're just going to wait a minute for people to join, and then we'll start. Good morning. All right, let's start. So, all right. So, last class we talked about. We ended class with set theory. So, last class we ended with a discussion on set theory. Okay, and so in set theory we talked about several different things. We talked about sets, subsets, union, intersection, complementation, and complementation. So these are the 5 things we talked about in set theory, right? So I gave definitions and I gave Venn diagrams, which were picture illustrations of these 5 things, right? Okay, so that was how we ended last class. So this class, we're going to continue this discussion on set theory. So we're going to continue set theory, and so that will include so that will mean talking about the empty set. So we're also going to talk about disjoint sets. People are still joining. Disjoint sets and mutually exclusive sets, mutually exclusive outcomes. Okay, and then other facts, other useful facts. Okay, set theory, and so we'll also talk more about Venn diagrams. Okay, and so we will also talk about the axioms of probability. Okay. And so there are also some theorems that we're going to talk about. And that's if we have time, which we probably will. All right, so let's get started. Okay, so after complementation, the 6th thing to talk about is what's called the empty set. Okay, so here's a definition of the empty set. You can all hear me, right? Okay, good. And you can all see the screen with Word. Okay, so the definition is the empty set is the set of no elements. Okay, so we use what's called the null set symbol. So we use that symbol to denote the empty sets. Also, you can also use just braces with nothing in it, also to denote the empty sets. Okay. Note that the empty set is equal to the complement of the universal set, S prime, where S here is the universal set. So if the universal set S is the set of all elements under consideration, its complement has to be nothing. And so the empty set is equal to the complement of the universal set. All right. Okay, so the empty set is the outcome that none of the simple outcomes represented by sample points in the sample space occur. Okay. 7 is on disjoint sets and mutually exclusive outcomes. Now remember, an outcome is a subset of the sample space, right? The sample space is the set of all simple outcomes. All right, so you have the sample space is the set of all simple outcomes. And then you have an outcome as any subset of the sample space. Okay, A and B are disjoint sets if their intersection is empty, is equal to the empty set. Okay, so if two sets do not intersect, if their intersection is the empty set, they're called disjoint sets. So the way to illustrate that would just be if you have this set here, A, and this set B here, and they don't intersect, their intersection is equal to the empty set, and so they're disjoint sets. Okay. Now in a Venn diagram, the circles could overlap maybe, but there'd be no elements in the intersection. So another way to draw this would be you have one set here, you have another set here, right? But when you put in the elements in each set, you might have an element from A here, you might have this element here, you have an element here, you have an element here, maybe an element here, but there's nothing in the intersection, so they're disjoint, right? But having the circles drawn like this separately just makes it obvious that there's nothing in the intersection. So these are two ways to illustrate that sets A and B are disjoint, that their intersection is empty. Okay. Okay, so that's the definition of disjoint sets. Okay. Another definition. If A and B are outcomes and their intersection is empty, then they cannot occur simultaneously and are called mutually exclusive. Okay, so A intersection B is equal to the empty set means that outcomes A and B are mutually exclusive. Okay. An example of this would be roll a fair six-sided die. Okay, let's say A is the event of rolling an even number, and B is the event of rolling an odd number, right? These two events cannot occur simultaneously. They can't happen at the same time. You can't roll a die and roll both an even and an odd number. So A and B here are mutually exclusive outcomes. Make sense? Okay, so the two outcomes that cannot happen at the same time, for the sets, as sets, they're disjoint. Okay, definition. A sequence, A1, A2, A3, ... of outcomes. So a sequence of outcomes is mutually exclusive if A sub I intersection A sub j is equal to the empty set for any two different ij. So for I not equal to j. And right, the I and j are both in the set of positive integers. So the set 1, 2, 3, 4, 5, ... I'm just going to move this here so this doesn't, so this is all together. Okay, so a sequence A1, A2, A3, and so forth of outcomes is mutually exclusive if the intersection of any two of them is empty, meaning any two of them are disjoint, are mutually exclusive. And so I'm just, the notation is A sub I intersection A sub j equals the null empty set for I not equal to j and I and j being positive integers. Make sense? Okay, so this is just the mathematical notation for that. All right, so another okay, good. So that was 7. So 8 is on other useful facts about sets and outcomes. Okay, so A is A union B is equal to B union A. And also A intersection B is equal to B intersection A. I'm just going to separate those two. So these are two examples of the commutative law. Okay, so the order doesn't matter. So when you take the union of two sets, it doesn't matter the order. So A union B equals B union A. And when you take the intersection of two sets, that also doesn't matter. So A intersection B equals B intersection A. Order did not matter. And so that's the commutative law. Okay, B, getting a little more advanced here. A union B union C is equal to A union B union C. Okay, and also you do the same thing for intersections. So A intersection B intersection C is equal to A intersection B intersection C. Okay, so see, the only thing that changed was where the parentheses were from the left and right side. So here on the left of this equation, the parentheses is here, and on the right side, you move the parentheses here. So the sets are the same, the operation is the same, but the order that you do the operations is different, right? But you still get equality. And so the same thing happens here. You move the parentheses, you change the order of the intersections here. First, you intersect these two, then that, and then here you intersect these two, and then this. And that's called the associative law. Okay, and so that doesn't matter either. You can move the parentheses when these operations are the same on both sides. You can move the parentheses and it doesn't change anything. Okay, so because of the associative law holding, we do not need to use parentheses in these two situations, right? In other situations, you need them, but when you just take the union of three sets or the intersection of three or more sets, you don't need parentheses in that situation. And so we can use the notations. So we can use the notations A union B union C, and we can also use A intersection B intersection C, instead, just without parentheses, because both of them, both the orders are the same. Okay. Okay, so because of A and B, you can use that without. And also remember that when that is also is another way to say A intersection B intersection C. Okay. So a faster way to write this is without parentheses and without the intersection symbol. So ABC would be, you can use that also because of this. Okay, good. So C is, so we have these equations. So if we have A union B intersection C, then that's equal to A union B intersection with A union C. And also, now we can also switch the operations, and so we have A intersection B union C is equal to A intersection B union A intersection C. Okay, so these are two examples of what's called the distributive law. Okay, so here with this equation, you can see that I'm taking A union B, and then the intersection symbol ends up here, and then it's A union C. And here it's A intersection, and then intersection B union A intersection C. Okay. Okay, so let me quickly, I'm going to go to the whiteboard again. So let's illustrate the distributive law here. So okay, so you have the universal set, and we have three sets, A, B, and C. A, B, C. Okay, that circle is closed. Okay. So if you have A union B intersection C, so A union B intersection C. So I'm actually going to denote this with the purple here, the pink here. So A or B intersection C. Okay, so this is A, but not just that. So this is still in circle A. Right? These are just regions that overlap with the other circles, but they're still in A. So that's A. And then you're unioning it with B intersection C. So B intersection C is these. We already have this covered. It's union. So we're just going to include this part here. So that's A union B intersection C. Okay. And then so you see how A union B intersection C is that. And then A, B, C again. Now let's illustrate A union B intersected with A union C. Okay, so it's an intersection. So A union B is an A or B, right? But you want to look where A union B overlaps with A union C. So this region is in A union B, right? And it's also in A union C. This region is not in is an A union B and an A union C. See that this little part is an A union B and it's an A union C. This part here is an A union B, but not an A union C. This is an A union B and A union C. Okay. This region is an A union C, but not an A union B. This region is A union B and A union C, so I'm including that also. Okay, and so can't include these two, but these two you do. So this is the region A union B intersection A union C, and you see that they match up, right? And so what we just showed here is that these two sets are equal by using Venn diagrams. Okay, and so you can see how those two sets are the same. Okay, and so there's also the other distributive law, and you could do the similar, you could do the same kind of thing there to show that that equals, those two are equal. Okay, so next is D, and so D, if you take the complement of the universal set, like we said earlier, you get the empty set or the null set. Okay, if you take the complement of the empty set, you get the entire universal set. And if you take a set A and you take its complement, and then you take the complement of the complement, end up back with A. Okay, so these are three more useful things to know. Okay, so that's D. E, if you take a set A and you union it with the universal set, you get back the universal set. If you take A intersected with the empty set, you get the empty set. And this is for all subsets A of capital S. F, if you take a set A and you union it with its complement, you get the entire universal set S. If you take a set A and you intersect it with its complement, you end up with the empty set. And then G, if you take A union B and you take its complement, that's equal to the complement of A intersected with the complement of B. And also, if you take the intersection of two sets and you take its complement, that's equal to A complement union B complement. Okay, and so these two equations in G are called De Morgan's laws. Okay, so G, these two equations, these two are called De Morgan's laws. And it's just saying the complement of A union B is A prime intersection B prime, and the complement of A intersection B is A prime union B prime. Okay, so those two laws, so they look weird, are very important. So I'm going to illustrate those also with Venn diagrams. So, okay, so you have the universal sets, and so here's set A, and here's set B, and so let's illustrate the fact that A union B prime is equal to A prime intersection B prime. So A union B would be what's in either circle. So A union B prime. So A union B prime would be anything not in the circles, right? So A union B is here, its complement is everything outside of the two circles.
Professor,
Yeah,
what about A intersection B?
right. So that's a separate one, right?
Yep.
One De Morgan's law says A union B prime equals A prime intersection B prime.
Yes.
Okay, I'll show you that one. Okay, so so now let's look at another Venn diagram. So then, so let's look at A prime intersection B prime. So A prime intersection B prime means A prime means everything not in circle A, and B prime means everything not in circle B. So A prime intersection B prime would mean everything not in A and not in B. So everything that's not in A and not in B is the same region, right? So they both represent the same regions, and so they're equal. Okay, so those two sets are the same. And then the other De Morgan's law would be A intersection B prime. So you have set A, you have set B. And so A intersection B is where the two circles overlap. And so the complement of where they overlap is everything, every other region other than where they overlap. And so you get this, right? You get everything outside of the overlap. And then here, we have, let's say you have A prime union B prime. That's a prime. So then you have circle A. You have a circle B. Okay, so A prime would be everything not in circle A. We're taking the union, so I can think of one at a time here. That's A prime, right? So that's everything not in circle A. And then union B prime, everything not in circle B. So that includes this also. And so A prime union B prime is the same as A intersection B prime. And so these two sets are also equal. So these two are De Morgan's laws. And so these Venn diagrams are showing that the two De Morgan's laws hold. Okay, that makes sense. Okay, so I think that answers the question. Okay, good. So the next thing we're going to talk about is just Venn diagrams. And so let's see the whiteboard for this. Okay, so I already showed some Venn diagrams, so what I'm going to do is show some more. Okay, so I already said out loud these things, but I want to say them explicitly, right? So if you have sets A and B, their intersection would be this, right? Their intersection would be in the middle part. So I was saying that as I was drawing it, this is A intersection B. Okay. So another important thing is A complement, right? So I said it while I was drawing it before. If you have your universal set S and you have the set A in it, A complement would be all the elements not in set A, right? So that would be this set here. Okay, and then if you have disjoint sets, right? I already said this before, but if you have two circles C and D and you draw them like that, that means this is one way to illustrate that two sets are disjoint. right? Or that their intersection is empty. Another way to illustrate it, I'm not doing anything here. I'm just just separating, but I'm separating it. I'm kind of still talking about the same thing. Or you could write it like this and like this, right? You have C and D. Now, if you call these different sets, so let's say this is set E and set F. And so let's say in the intersection, there's something in the intersection. Okay, it's not empty. And so, so E intersection F not equal to the empty set, not empty, implies that E, F are not disjoint. Okay, so E and F as sets are not disjoint when their intersection is not empty. Okay, so their intersection not empty, something being in the intersection implies that they are not disjoint sets. But here they are disjoint because there's nothing in the intersection. They don't overlap, right? Okay. Okay, so that's the stuff I wanted to talk about with Venn diagrams here. And so one more thing for this section. So we're going to use, we use results, outcomes, and events interchangeably to mean the same thing. All three words / terms mean a subset of the sample space. Okay, so before I defined an outcome to be a subset of the sample space. And so there's two other words that are used to mean the exact same thing, and that's results and events. So an event is a subset of the sample space, and a result is also a subset of the sample space. It's the same thing as an outcome, which I already described is a subset of the sample space. Okay, so whenever you see result, outcome, or event, all three of them mean the same thing, a subset of the sample space. Okay. Okay, so 1.4 is on rules of operation for probability events. Okay, definition. An axiom is a statement that is assumed to be true. Okay, so in the foundations of probability theory, of axiomatic probability theory, we have axioms or statements that we assume to be true. So those statements, we build on them to build probability theory. Okay. A theorem is a statement that can be deduced either from axioms or from previously proved theorems. Okay, so you start with axioms, then you deduce from your axioms, theorems. And then later, you deduce more theorems from the theorems you already have or from still the axioms. Okay, so in probability theory, we put an axiomatic probability theory, which is what we're doing in this class. In axiomatic probability theory, you assume several simple statements concerning probability. these simple statements called the axioms of probability. Okay, all other statements made in our study of probability are deduced from these axioms. They are called theorems of probability. Okay, so such axioms and theorems are the rules of operation for the mathematics of probability. So once you have your axioms, which are your assumptions, and you have the theorems that you deduce from your axioms, but once you deduce a theorem, once you have an assumption and an axiom, you're held by that assumption or you're held by that theorem. So when you do math later, you can't contradict any of the assumptions you made in the beginning or any of the theorems you deduced from those axioms. Okay, so the more things you prove, the more things you know, but the more things you're bound by as you move forward, right? There's restrictions, there's things you can do and there's things you can't do, right? There's things you know you can't do, there's things you then know you can do. So, okay, so everything has to make sense, but you also now have to live by these rules to move forward. Okay, the probability of an event is a number between 0 and 1 inclusive. Inclusive meaning it could also be 0 and 1. Okay, so we assign numbers called probabilities to sets called events. And these, when you call it event, you could also say it's or called outcomes or called results, right? Just like I said, just very short over here, right? Okay. So the probability of an event is a number between 0 and 1 inclusive. We assign numbers called probabilities to sets called events or called outcomes or called results. Okay. Probabilities, therefore, are values of a set function, capital P, that assigns numbers P equals the probability P of A to events A of a sample space S. Okay, so I feel like this is important. So what I'm going to do is I'm going to bold it. Maybe that makes it hard to read, so I don't want to bold it. Maybe underline it. I'll do that. Okay. Okay, so the probability of an event is a number between 0 and 1 inclusive. We assign numbers called probabilities to sets called events. Probabilities, therefore, are values of a set function P that assigns numbers, little p, which is equal to P of A, to events A of a sample space S. Okay, so what does that mean, right? So let's say as an experiment, you have rolling a fair 6-sided die, right? So when you say the probability of rolling an even, the probability of rolling an even number is equal to 3/6, which is 0.5, right? When you say that, what you are doing is assigning the number 0.5 to the event of rolling an even number. Okay, without realizing it, you've now assigned this number 0.5 to the event of rolling an even number, right? Saying the probability of rolling an even number equals 0.5 is really just assigning a number to an event, right? This equal sign here, it's equal to this thing we created called a probability function, okay? So if you have an event right? How is an event related to a number, right? We're assigning the number to that event. Technically, when you look at rolling an even number, there's no 0.5, right? We're assigning the number to that event. We're saying when you think of the event of rolling an even number, now associate the number 1/2 to that event. And we're doing it by this probability function. Okay, it's called a set function because we're taking a set and we're assigning a set to a number. Okay, so here where I said we assign numbers called probabilities. So here, 0.5 is a probability. And as a number, we're assigning that number to this event. So we assign numbers called probabilities to sets called events. So probabilities, therefore, are values of a set function P that assigns numbers little p to events A of a sample space S. Okay, so what's happening here is that this is called the machine diagram representation of a function. So the function is the machine here. And so you have an input and you have an output for this function. Okay. This function has one input and one output. So this is the probability function P, right? But the input of this function is an event E, and the output is a number. And so in this example, so in that example, okay, so in that example, the event E is the event of rolling an even. Right? And here, the number is 0.5 or 1/2. I guess we'll put 0.5. Okay, so this function, we inputted an event. Rolling an even is an event, right? It's the set 2, 4, 6. It's an event because it's a subset of the entire sample space 1, 2, 3, 4, 5, 6, right? This is the sample space. 2, 4, 6, the even numbers, is a subset of the sample space. And so this is an event. And so we input an event into this function and we output a number. We're just assigning this number 0.5 to this subset of the sample space, an event of rolling an even. And so P here is a function. So this probability, this is the type of function this is a set function. And it's a set function because the inputs of this function are sets. You would only input a set into it. But specifically, you have to input a subset of the sample space into it. But every subset of the sample space is a set. So this is an example of a set function. Okay, a set function. FCN is an abbreviation for function. Okay, so that's an example of a set function. Okay, so that's explaining this part here. Okay, so definition. A set function, P, that assigns numbers, little p is equal to capital P of A, to events, capital A, of sample space, capital S, is called a probability set function or a probability measure if the following axioms are satisfied. Okay, so it's a set function because the inputs are sets, but now we're going to talk about a probability set function, which has a little bit more structure to it. And so in order to be a probability set function, in order to be more than a set function, to be a probability set function, you need to satisfy the following axioms. So axiom 1 is that the values of P of A are between 0 and 1 inclusive for all events, capital A, of the sample space, capital S. axiom 2 is that the probability P of S is equal to 1. And so if you input the entire sample space into the set function P, the output has to be 1. That's the second axiom. And then the third axiom has two parts. If A and B are mutually exclusive events, then the probability of A union B is equal to P of A plus P of B. Okay. Remember, P is a set function. The inputs are sets and the outputs are numbers. And so if P of A is a number and P of B is a number, we can add them. Okay. But this property is saying that if A and B are mutually exclusive events, then P of A union B is equal to P of A plus P of B. Okay. So that's that statement. If part B of axiom 3, if A1, A2, A3, and so forth is a finite or infinite sequence of mutually exclusive events of the sample space capital S, then P of A1 union A2 union A3 union ... is equal to P of A1 plus P of A2 plus P of A3 plus ... Okay, so the probability of a union of a finite or infinite sequence of mutually exclusive events is equal to the sum of the respective values under P. Right, so you get this equation. That's B. So if axiom 1, 2, and 3, meaning A and B in axiom 3, if all of these things are satisfied by the set function, you can call it's then a probability set function. Okay, and if P, this probability set function, assigns the value / number little p, which equals P of A, capital P of A, to the events capital A, then we say that little p, or P of A, is the probability of event capital A. Okay, so now P of A, which is known by little p, is the probability of the event A. Once it's established that this function P is a probability set function, its values are probabilities. Okay. Okay, so 1.4.2 is on elementary theorems. Okay, if you have any questions, you can just turn on the mic at any time and just ask. Okay, so don't be shy. Okay, so the following theorems are derived from the axioms of probability. Anyone have any questions at this point? Okay, so the following theorems are derived from the axioms of probability. So theorem 1.1 says that probability of the empty set is equal to 0. Okay, so the proof of that is this: if you have the empty set, right, and you union it with S, it's equal to S, right? But that implies that the probability of of the empty set union S is equal to P of S, right? Because the empty set union S is equal to S, and that's equal to 1. So, okay, so that's equal to 1. But so the P of S, equaling to 1, that implies that P of the empty set P of the empty set union S is equal to P of the empty set plus P of S, and that's equal to P of the empty set plus 1 Okay, so I'm going to denote this by 1. We're going to denote this by 2. This P of S equals to 1. And we're going to denote this last equation by 3. So combining 1, 2, and 3, we get, so what we get is that P of the null set plus 1 is equal to P of the null set plus P of S, which is equal to P of the null set, the empty set, union S, which is equal to P of S, which is equal to 1. Okay, and so then that implies that P of the empty sets plus 1 is equal to 1, and that implies that P of the empty set is equal to 0. Okay, so if the empty set union S is S, then that implies that the probability of the empty set union S is equal to P of S. P of S is 1. That implies that P of the empty set union S equals P of the empty set plus P of S, because they're mutually exclusive events, right? The intersection of the empty set and S is the empty set. And so then this is equal to P of the empty set plus 1, because P of S is 1. That's 3. And so if you combine all 3, you get P of the empty set plus 1 is equal to P of the empty set plus P of S. And so then that's equal to P of the empty set union S. And so that's equal to P of S, and that equals 1. And so therefore P of the empty set plus 1 equals 1. And so P of the empty set is 0. Okay, and so now we have that is proved. Okay, so theorem 1.1 is proved. Okay, so theorem 1.2 is that P of A prime is equal to 1 minus P of A. Okay, so the proof of A, the probability of A complement is 1 minus the probability of A. And so the proof of that is if you have A union A prime, that's equal to the entire sample space. And that implies so that implies that P of A union A prime is equal to P of S, which is 1. Which is equal to P of S.
Professor?
Yeah?
I have a question about the proof that you just did.
Proof of 1.1?
Yes.
Okay, yeah.
So you know how you went you know how you went from like P of the empty set plus 1 equal 1? Like the line before the last line. How
Here?
no, like under. Yeah.
Here, yeah.
Yeah, so where did the 1 go? Like you went from P of the empty set plus 1 equal 1 and then P of the empty set equals 0.
Oh, you mean because you just subtract 1 on both sides?
Oh, right. Okay.
Make sense?
I just didn't see it. Yeah, I just didn't see that for some reason.
Sometimes the easiest thing you don't think of because you're looking at all these probabilities, right? And so you're not thinking about subtracting 1 on both sides. So yeah, it's just simple subtraction of 1 on both sides. That's all.
Right. I was just trying to see the whole picture of.
Okay, it's like if you had an equation x plus 1 equals 1, you'd solve for x, and it would be 0. Here, the variable is P of the empty set.
Right. Thank you.
You're welcome. So in math, right, even though when you had equations in algebra, you would use like x or y and you would solve for it, right? You can still have those situations where instead of x or y, you have the probability of something, right? So P of the empty set is an unknown. And so that's just an equation with an unknown, and you solve for it and you get 0.
I have a question.
Okay. So theorem 1.2, P of A prime equals 1 minus P of A. So the proof, so the probability of A union prime equals P of S. And so we'll call that 1. P of S is equal to 1. Okay. Call that 2. And okay. And then P of A union A prime is equal to P of A plus P of A prime. And so we'll call that 3. That's just because they're mutually exclusive, right? Events A and A prime are mutually exclusive. And so combining 1, 2, and 3, we get, so we get is that P of A plus P of A prime is equal to P of A union A prime. That's equal to P of S, which is equal to 1. And so that implies that P of A plus P of A prime is equal to 1. And that implies that P of A prime is equal to 1 minus P of A. That's just solving an equation normally, right? So you just subtract P of A, which is a number, on both sides. And you get P of A prime is equal to 1 minus P of A. Okay, and so we just proved that P of A prime is equal to 1 minus P of A. And so here, theorem 1.2 is proved. Okay. Any questions about the proof of theorem 1.2? Or theorem 1.2? No. So the next theorem is theorem 1.3. which is P of A union B is equal to P of A plus P of B minus P of A intersection B, which we're going to write AB here to help you get used to the notation, right? And so, reminder, AB is notation for A intersection B, right? And you can do that for any number of sets and any set. So AC would be A intersection C, ABC would be A intersection B intersection C, right? Where parentheses doesn't matter because we showed earlier that that doesn't matter. Okay, so proof. Okay, so we will use the no. Oh, all right. Okay, so proof. Statement 1. So I'm going to break this proof down into several parts. So the first part is going to be to prove this statement: A union B is equal to AB prime union AB union A prime B. What? Blah. Sorry. I mean, no, I'm not gonna. I'm not proving that statement. I'm using it. So that equation holds. That equation is true. And so what that implies is that the probability of A union B is equal to the probability of that set right here. I'll explain why. Okay, so I'm doing it in out of order, which is the best order to explain it. So A union B is equal to the union of these threats with these three sets. So that means the probability of this set is equal to the probability of that set. And so that's what I wanted to prove. That's what I wanted. Statement 1 is that. Okay, so if you take this set equals that set, therefore the probability of the left side equals to the probability of the right side. And so why is that true? So maybe write this down at least. And so I'm going to go to the whiteboard in a second. So A union B equals the union of these three sets: AB prime union AB union A prime B. And this looks complicated, but it's very simple. So, okay, so let's say you have your universal set S, and so you have your sets A. Oh, this is a good circle too. You have your set A, and you have your set B. Okay, and so you have AB prime union AB union A prime B. Okay, so okay, actually I'm gonna use colors here. So let's go with A B prime union AB union A prime B. Okay, so we have this union of three sets. And so we're going to see what this is. A B prime is everything in A that's not in B. That's this. AB is the elements in both sets AB. It's that. And then A prime B is everything not in the circle A, but in B. And so you get that. So that's AB prime union AB union A prime B. And so what are the union of those three sets? It's AB, A union B. See that? So A union B is equal to AB prime union AB union A prime B. Very simple. Okay, and so since those two sets are equal, their probabilities are the same. Okay. So A union B is equal to union of these three sets. Therefore, P of A union B is equal to P of the union of those three sets. Okay, statement 2. Okay, so statement 2 is going to be P of A is equal to P of A B prime union A B. Okay, and so that's just from the fact that the set A is equal to AB prime union AB. Okay, that implies that these two sets are equal. I mean, these two numbers are equal. These two probabilities are the same. Okay, since A is equal to AB prime union AB, that implies that P of A is equal to P of AB prime union AB. Okay, and so what I'm going to do in the whiteboard now is show you this equality of sets. Okay, so in the whiteboard, I'm going to show you this, and then, but you can see how that implies that P of A is equal to P of that's on the right. So let's do that. So you have the universal set again. You have A, you have B. Okay, and so if you look at AB prime, I'll use colors again. If you look at AB prime and you union it with AB, then what you get is AB prime is this part and AB is this part. And so you take AB prime union AB and you get A. Right? So you see how A is equal to AB prime union AB. Okay, so we have this equal quality of sets. And so that implies that P of A is equal to P of AB prime union AB. Okay, so that's statement 2. Okay, and then statement 3. Statement 3 says, what I want to show with statement 3 is that P of B is equal to P of AB union A prime B. This is very similar to statement 2. We're kind of reversing the roles of the set. So B is equal to AB union A prime B. And that implies that P of B is equal to P of AB union AB prime. Union A prime B. Okay, and so on the whiteboard again, I'm going to show now this. On the whiteboard, I'm now going to show this equality. And so when I show that equality of sets, that will imply that P of the left-hand side set is equal to P of the right-hand side set. And then we'll have statement 3. Okay, so this is going to be the goal of the whiteboard in a second, in a few seconds, to show that. Okay, and you see the logic of how you can apply that from that. Okay, so then, okay, so if you have the universal set S and you have A and you have B, and so if you look at AB union AB union A prime B, then this is what you get. So AB is the intersection of the two sets. And A prime B is what's not in circle A, but still in circle B. And that's this. So AB union A prime B is equal to B. Okay? So B is equal to AB union A prime B. And so P of B is equal to P of AB union A prime B. Okay? And so that's how we get that. So that's statement 3. So we have these 3 statements. This is equal to this is equal to this, and that's equal to that. So using statements 1, 2, and 3, and axiom 3, we get, and so what was axiom 3? Axiom 3 was this, right? Okay, so we want is we want is part B of axiom 3. Right? Reminder. Part B of axiom 3 said this. Just make sure I didn't delete it. Good, sorry. Good. Okay, so part B of axiom 3 said this. If you had a finite or infinite sequence of mutually exclusive events of S, then P of their union is the sum of their P's. Okay, so using statement 1, 2, 3, and part B of axiom 3, we get the following. So we get, first we start with P of A union B. Remember, the goal is to show that P of A union B is, no, we want to show that P of A union B is equal to P of A plus P of B minus P of A intersection B, right? This equation. That's the goal, right? Okay, so we're starting with P of A union B because it's the left-hand side of this equation, and the goal is to say this is equal to the right-hand side of the equation. Okay, so first you have that P of A union B is equal to P of this. Right? And so this is by statement 1. Right? Statement 1 tells you this equals this. So next, that's equal to now P of AB prime plus P of AB plus P of A prime B. And that's by axiom 3, part B. Since the sets involved, since A, B prime, AB, and A prime B are mutually exclusive events. Okay. Earlier, when we talked about AB prime, AB, and A prime B, we showed that they were different. They're not overlapping. Here, AB prime, AB, and A prime B, right? These 3 different code sets, they don't overlap, right? And so as events, they're mutually exclusive, right? So this set, and this set, these 3 sets are mutually exclusive. Okay, so these 3 sets are mutually exclusive events because these 3 events are mutually exclusive. They don't overlap, right? None of them can occur at the same time. Okay, so good. Okay, so part B of axiom 3 said if you have a finite or infinite sequence of mutually exclusive events of S, P of their union, P of the union of 3 mutually exclusive events is the sum of the 3 probabilities. So that's by part B of axiom 3. Okay, and so now that's equal to and so now what I'm going to do is something weird. I'm going to take the same exact thing. It's equal to itself plus P of AB minus P of AB. Okay, so I just added a quantity. P of AB is a number. So I added that number and then subtracted the same number. And so they're still equal. Okay, so why did I do that? So the reason I did that is because now I'm going to move around the terms. So okay, so if you have the P of AB prime plus P of AB, because we have this and this, right? So we have this term and we have this P of AB here. And so that's this plus this here. Okay, so then plus P of A prime B plus P of AB right? So we have two P of ABs here, here and here. We added this one and then subtracted it, right? So now this plus this P of A prime B plus AB. Actually, okay. I'm going to use this P of AB here for the red. Okay, so this plus this is this, and then this I'm going to use blue. This I'm going to use blue. Okay, so we have the sum of these two things plus the sum. Oh, I guess. Oh, actually, no, this is good. You know what? I'm writing the same thing, but that's all right. And then minus P of AB. Okay, so I haven't done it. So I didn't do anything in this step. I'm just coloring it in. Oh, wait, I guess technically, I guess we don't need that. Okay, so so I added and subtracted right here. That's what I'll do since I spent the time doing that. So we added and subtracted P of AB here, right? So we ended up with the same thing. Now I'm just coloring it in. So if now look at these two, and you have this at the end. So then, we have by statement. Okay, so P of AB prime plus P of AB, that's equal to P of AB prime union AB, right? Because so this AB prime and AB are mutually exclusive events, and so P of their union is equal to sum of their probabilities. That's by axiom 3 part B. And so here we have P of A prime B there we go. A prime B union AB. And so then this right, these two events, A prime B and AB, are mutually exclusive. And so probably the union is the sum of their probabilities. And then And so then it's minus P of AB, right? And so this is by axiom 3, part B. And that's because we have mutually exclusive events. Because events are mutually exclusive. Okay, and so now in statement 2, we had P of AB prime union AB is equal to P of A. And so here we have P of A plus P, in statement 3, we had P of B is equal to P of AB union A prime B, right? So the commutativity, we can just switch the order of that, right? And that's P of B, and then minus P of AB at the end. So this was from this is associating with the red part. This I'm associating with the blue part. Okay, and so there you go. P of A union B is equal to P of A plus P of B minus P of AB. And so the proof is done. Okay, so theorem 1.3 is proved. Right, that was theorem 1.3. And so we now proved it. We said that this is equal after the string of, after this chain of equal signs, we get that is equal to this. Okay. So we go to the whiteboard a second and we look at why this makes sense. So you have the universal set S. Okay, you have the set A. You have the set B. Right? If you were to think of the equation we just talked about, right? Our equation is P of A union B is equal to P of A plus P of B minus P of AB. Okay, well, for if we looked at P of A, right? If we looked at P of A, right, we would have P of A would say, what's the probability of something here, right? And then for P of B, it would say, what would be the probability of something in B, right? But then if you notice, the middle part, we counted twice, right? We counted the middle part as part of the probability of A, and we counted the middle part as part of the probability of B. And so when you subtract the probability of AB, you're getting rid of the overcount, right? You're getting rid of the fact that we counted this twice. And so if you count these things once, you count these things once, and you count this thing twice, and then subtract one, so a net once, then you're finding the probability of A union B. Make sense? The subtraction here is to get rid of the over counting, how we considered this region twice, because there was an overlap here. Okay? Okay, so then that's how you can visualize that equation, this equation here. Okay, so then this, okay, so that's the proof and how you visualize the conclusion, right? Okay, so now example 1.5. Events A, B, C. Events A, B, and C have probabilities P of A, which is equal to 1/2, P of B, which is equal to 1/3, and P of C, which is equal to 1/4. Okay. Furthermore, the intersection of A and C, A intersection C, is equal to the empty set. And B intersection C is equal to the empty set. And P of A intersection B is equal to 1/6. Find, so in part A, we want to find the probability of A intersection B, which I'm going to denote as AB prime. So it's the prime of A intersection B. Okay, so the prime of A intersection B is 1 minus P of AB. Right? And so that's equal to 1 minus, well, P of A intersection B, P of AB is 1/6. This is 1 minus 1/6. That's equal to 5/6. Right? As a decimal, that's equal to 0.833, so forth. So 0.833 round this nearest thousandth. I like fractions more because fractions are more illustrative of a number than decimals, right? 5/6, 5/6, you visualize what 5/6 is. You don't really visualize what 0.833 is. Okay, so yeah, so 1/6 is 0.1666. So I just did 1 minus 0.166 and got 0.833. Okay, so that's A. B, probability of A, B prime, which is A intersection B prime. So what is the probability of A intersection B prime?
I have a question.
Yeah.
So can you explain how you get like the value for part A? Can you like repeat the step?
Sure. Okay. So the question is, what is the probability of AB prime, right? That's the complement of AB, right? So we know that we said earlier that the probability of an event C, I'm using C, just a different letter, that with the probability of C prime, the complement of a set of an event C prime is equal to 1 minus P of C. Remember that?
Yeah.
So AB is used in place of C. So P of AB in parentheses prime is equal to 1 minus P of AB. Does that make sense?
Yeah.
Okay, and then what is P of AB? It's 1/6, right? AB is shorthand for A intersection B. So here you're given as an assumption that the probability of AB is 1/6, and so I just substituted. So it's 1 minus 1/6, which is 5/6. As a decimal, it's 0.833.
Okay, thanks.
That makes sense?
Yeah, thank you.
Okay, you're welcome. Okay, so in B, we want to find P of AB prime. And so that's equal to P of A minus P of AB. And so the reason for that is that since we have that P of AB prime plus P of AB is equal to P of A. This goes back to the proof we just did in Theorem 1.3, right? When we said P of A is equal to P of AB prime union AB, we had A is equal to that, right? And so that's from here, right? I'll show this again, but because you have this, just subtract P of AB on both sides. So if you subtract P of AB on both sides, this goes away. And you're left with P of AB prime equals P of A minus P of AB. So you just subtract. So then subtract. And then you subtract P of AB on both sides equation. PQN is the abbreviation for equation. Okay, so and you just subtract that quantity on both sides. Okay, and this is from before. Right, so here we had, right, A is equal to AB prime union AB, right? So these are sets of the same. So P of A is equal to P of AB prime plus P of AB. They're mutually exclusive, and so it's from that. P of A is equal to P of this plus P of that. You subtract P of AB on both sides. Okay, so we now have this equation here. Okay, and so now that we have that, well, P of A is 1/2, right? So P of A is 1/2, so we just substitute. Then minus P of AB, which is still 1/6. 1/2 minus 1/6. This is by substitution of given probabilities. And so then that's equal to 1/2 is 3/6. 3/6 minus 1/6 is 2/6. That's equal to 2/6, which is 1. Okay. That's just by subtraction. Okay. And so the answer to part B, P of AB prime is 1/3. Okay, and then C, P of A union B prime is equal to 1 minus P of A union B. And so then P of A union B is equal to P of A plus P of B minus P of AB, and this is by theorem. This is minus P of AB. It's by theorem 1.3. Right? So that's by theorem 1.3. And so P of A union B. So now you just substitute values. Given values, so P of A is given as 1/2 plus P of B, which is 1/3, minus P of AB, which is 1/6, which is 1/6. This is by substituting given probabilities. And so then you just add and subtract. And so 1/2 plus 1/3 minus 1/6, that's 3/6 plus 2/6 minus 1/6, right? So that's 3/6 plus 2/6 minus 1/6. That's equal to 4/6, and that's equal to 2/3. Okay, and that's by arithmetic. Okay, so you get that the answer is 2/3. Okay, I mean, sorry, you get P of A union B is equal to 2/3. And so this is equal to 1 minus 2/3. P of A union B is 2/3. And so 1 minus 2/3 is 1/3. And then that's the answer. Okay. Okay, so this is the answer. Okay. So this is by This is by star, where this is star. Okay, so star is this stuff, and so by star, you substitute P of A and B is 2/3. Okay, and so that is part C. Okay, so next time we'll finish this. We'll do some more examples, and then we'll just keep going. Okay, so I'm gonna end class here. That's it for today. I got everyone for attendance in the class. So everyone is marked as present, so we don't have to worry about marking attendance anymore. And I'll see you tomorrow. I'll see you. Wait, today is Thursday, so I'll see you on Monday, right? So we meet Mondays and Thursdays. So I'll see you on Monday at 10 a.m. Okay, bye everyone. Use the same class link from here on out.
I have a
You
question.
too. Have a good day.
I have a question.
Oh, sure. Yeah.
So far, like, I like the class. Like, the class is very interesting. Yeah, the class is very interesting. Like,
Oh, okay. That's good. I thought you had a question.
no, on how
Oh, okay.
you can comment.
Oh, okay. I'm glad you're interested in probability.
Yeah.
Good. Are you studying math? Are you a math major?
No, I'm like computer science major. Yeah.
Oh, okay. Are you using it for computer science, or you're just interested in probability?
Am I like use it for computer science, like probability and stats?
Oh, okay. There's another class after this in the master's level math. So if you like
Yeah.
probability, you might want to take that also after this.
Okay, yeah.
Sir?
But it's towards math. It would. I don't know if it would help you in the probability.
Okay.
It's a separate thing.
Professor?
Yeah.
Somebody else, sir. Can you post the slides on Blackboard as well? The whiteboard.
Oh, the whiteboard, right? Yeah. Okay. Thank you for reminding me.
Yeah.
I just saved it.
Yeah, and regarding 242, I might take that during spring as well for my math elective.
Oh, okay. Good.
Have a good day.
You too. Okay. Thank you for reminding me. Okay. All right. Okay. I'm gonna go. I'll see you on Monday.
Okay, thank you.
You're welcome. Bye.